Hello, this is Doug Snyder, and I'm the National Marketing Agronomist for SQM Specialty Plant Nutrition North America. And the topic we're going to discuss today is choosing the right potassium and nitrogen source for your crop. The three topics we're going to go through is an overview of the common potassium sources and their companion ion. We'll get into what a companion ion is in the presentation. And of course, the common potassium sources include SQM's potassium nitrate, muriate of potash, sulfate of potash, and potassium thiosulfate. We'll conclude our discussion with potassium sources and their effect on salt indices, the salt index. So with that, let's begin. Let's take a quick overview of the common potassium sources and describe what their companion ion is. Companion ion is the ion that goes along with the potassium. So in the case of the four sources you see here, potassium nitrate, the companion ion is nitrate. For potassium sulfate, thiosulfate, it's sulfur. And for potassium chloride, it's, as the name says, chlorine chloride. Now, the companion nitrogen ions we need to take a look at all four sources include the following. With potassium nitrate, the nitrate's already built into the product, so of course it's nitrate nitrogen. But potassium sulfate, thiosulfate, and chloride need a nitrogen source. That nitrogen source is generally urea, ammonium nitrate, ammonium sulfate, or in some situations, anhydrous ammonia. Selection of the nitrogen source depends on a couple of things: the plant physiology, as well as soil salinity conditions in the growing area. The key points to consider are sensitivity of the plant to ammonium. Some plants are more sensitive than others. The temperature range at the root zone, which makes perfect sense. The hotter it is, you might expect things to behave differently than if they were cool. The physiological stage of the plant. Are they in the vegetative stage? Are they in a reproductive stage? Are they in a vegetative going to a reproductive stage? And then finally, the presence of saline growing conditions in the cropping area. So let's discuss the sensitivity of the plant to ammonium. Nitrate is directly and more easily absorbed by the plant. What you can see in this little pictogram is that with urea type products, you can have issues with leaching or volatilization of the ammonium ion. Urea must go through a hydrolysis step in order to break apart the urea, into ammonium ions, which can either be adsorbed or desorbed by the soil colloids in the cation exchange capacity, and then eventually making their way to the plant. Some of this ammonium is also nitrified to become nitrate nitrogen. So you have both an ammonium ion and a nitrate ion going into the plant. Whereas with a pure nitrate source, that conversion step is not needed. The nitrate is available and ready for use by the plant and is upwardly mobile in the soil into the plant zone. Another thing that you can get into with ammonium is that since ammonium is a cation, there can be an antagonism in the uptake of the plant of key cations such as calcium, magnesium, and potassium because they're being inhibited by the other cation, ammonium. That doesn't happen with the nitrate ion because nitrate itself is an anion. So the anion, will tag along with the cation, the cations such as calcium, magnesium, and potassium, and travel with them into the plant. No antagonism, actually a synergism. So that can be a problem when you're looking at ammonium-based products versus a nitrate-based product. Another issue that can occur in certain species of plants, such as tomato, is that excess ammonium, because of that inhibition of calcium, can increase the incidence of blossom end rot, which is caused by a calcium deficiency in tomato, as well as many cucurbit crops that we'll talk about a little bit later. The second point that I'd like to consider when it comes to the selection of a nitrogen source would be the temperature range at the root zone. You have an increased risk of ammonium toxicity at elevated root temperatures because ammonium is more active and can cause ammonium damage, if you will, both in a hydroponic situation as well as in a soil-based or soil-to-soil media situation. You can see there on the left-hand side of the screen, when you're working with products that are only ammonium-based, that as soil's temperatures increase, the roots begin to be, you can see the decrease in root mass. However, with nitrate, that doesn't happen. So at elevated root temperatures, you don't have an ammonium burn of the roots like you will with ammonium, as you can see in the pictogram. The third thing to consider would be the physiological stage of the plant, as we discussed. Is it in the vegetative stage? Is the plant in the vegetative stage? Is it in the reproductive stage? Or is it transitioning from the vegetative to the reproductive stage? During vegetative growth, slight reductions in calcium and magnesium can't really be seen all that much, but during fruit development, calcium deficiency induced by ammonium can cause severe blossom end rot. We mentioned tomatoes earlier, also pepper plants, melons, and many other plants and many other vegetable crops. The last point to consider, as far as a key point, would be the presence of saline growing conditions. There's many parts of the country that are very familiar with saline growing conditions, primarily in the American West, and then that area primarily in California. However, saline growing conditions can occur anywhere. So it's something to consider when you're talking about your cropping system. A summary on the companion ion: that nitrate may be your preferred nitrogen source. It's non-volatile, it's easy to handle, and there's no need for incorporation. Nitrate is directly available for plant uptake, doesn't require transformation. Nitrate is mobile in the soil, so it can be easily uptaken by the plant, which is the most efficient use of the nitrogen source. Nitrates can promote the uptake of cations as opposed to antagonizing them. These issues have been confirmed by numerous research studies that increasing the ammonium to nitrate ratio negatively affects plant performance because of the antagonism of the ammonium to the uptake of cations such as calcium, magnesium, and potassium. We talked about the increased risk of ammonium toxicity at elevated root temperatures. It's also, the plant itself is able to convert nitrogen more easily to amino acids in the leaf, which leads to energy efficiency, higher use efficiency, and can lead to greater yields. Nitrate can relieve salinity stress caused by excess chloride, and we'll talk about that in a little bit, more in detail in a little bit. But nitrate counteracts the uptake of chloride, another anion. Crops fed with nitrate show an increase in water use efficiency, photosynthetic activity, and biomass production because of the point number 7, the conversion of the amino acids more efficient. The second area that we were going to discuss are the common potassium sources. We touched on them earlier: muriate of potash, sulfate of potash, potassium thiosulfate, And then once again, SQM's potassium nitrate. Everybody probably knows what muriate of potash looks like. Good old 0060. It's been around a long time and it's very commonly used and is a good candidate for potassium source. So let's take a look at potassium chloride, remembering that a major component of potassium chloride is chloride. There are crops that are sensitive to chloride. Many of the fruit crops are sensitive to chloride, such as apricots in California, avocado, citrus growers know this, peach growers in the southeast and south know this. Many of the nut trees, including almonds, walnuts, pecans, berries, including strawberries, vegetables like lettuce and sweet peppers, field crops, including potato and tobacco, coffee, and especially in horticultural crops, such as flowers. Chloride toxicity, you can see this in the picture. It's very easy to recognize in the soil. It looks like salt. That's because it is. Chloride increases soil salinity, which will affect root development, as well as water and nutrient uptake by the crop and the plant. Common symptomologies exhibited by chloride toxicity include marginal firing of the leaf with leaf tip burn. Generally, you see a general chlorosis of the end of the leaf, leading to a necrosis, a leaf burn, leaf tip burn, and along the margins as well. Very commonly, anybody that's familiar with any sort of chloride toxicity recognizes these immediately. Some people call it salt burn, but yeah, and it is. It's chloride toxicity. So remembering, as we talked about a minute ago, nitrate inhibits chloride uptake. Ammonium promotes chloride uptake. Why is that? Because nitrate is an anion, just like chloride. Ammonium is a cation. Cations and anions like each other and go into a plant together, whereas the nitrate will outfight, if you will, the chloride going into the plant. So the presence of nitrate antagonizes chloride uptake. The presence of ammonium will increase the uptake of chloride, which can lead to ammonium and chloride toxicity with the symptomologies that we described a little bit ago. Nitrate helps to relieve soil salinity stress caused by chloride. Quick little pictogram again. The nitrate is blocking out the chloride from going into the plant, and helping to alleviate excess chloride in the plant. So if we're working with plants and we're looking at a selection of products that contain chlorides, be careful of chloride sensitive crops and avoid chloride containing fertilizers. Let's take a look at the other products that we talked about. Sulfate of potash and potassium thiosulfate. Once again, remembering what we talked about a little bit ago, what is the companion ion of potassium sulfate and potassium thiosulfate? Sulfur. What can happen with excess sulfur? You can increase soil salinity as well as increasing calcium fixation. Calcium fixation with excess sulfur can cause the formation of calcium sulfate in the soil as well as in the fertilizer solution that we'll see in a little bit. Potassium nitrate has a 92% lower contribution rate to soil salinity than SOP, simply because potassium nitrate doesn't have sulfur in the product. Potassium nitrate, well-balanced nitrogen and potassium source. Taking a look at avocado nutrient recommendations, those are the general nutrient recommendations. 250 pounds of K2O, there's what you get with potassium nitrate. You can fulfill the entire ratio needed for K2O with potassium nitrate, some of the nitrogen needed with potassium nitrate, and not have any sulfur. However, when you're looking at avocado with sulfate of potash, when you fulfill the K2O recommendation with sulfate, you'll notice you have an excess of sulfur with SOP. If the plant's not going to take up that sulfur, it's just going to stay in the soil solution, leading to an excess sulfur buildup, which can contribute to excess salinity in the soil. We talked about this briefly earlier. Potassium nitrate's fully compatible with fertilizers and most agrochemicals. Potassium sulfate is not, because what can happen is a precipitate in that fertilizer solution of calcium sulfate. For those that have worked with sulfate of potash, they know that this can happen fairly easily, so they need to be very careful when mixing SOP as a fluid fertilizer because of the precipitation of calcium sulfate out of the fertilizer solution. It's tied up. It's very low solubility. It's not easily used by the plant. Blending capacity or capabilities, with many of the common fertilizers as far as solution is concerned, calcium nitrate or the CAN products, as well as with UAN, whereas SOP can have a problem with that. Another issue that you can run into with SOP is the dissolution rate of SOP versus potassium nitrate. Potassium nitrate solubilizes at a faster rate than SOP in the soil solution, not only the fertilizer solution like we just saw, but the soil solution as well. What we did was just do a quick visualization of putting these three products onto a media, which is fairly simple. It's just a wet sponge with a piece of paper on top of it, adding prills of the various products in a line and to see how rapidly they would dissolve. So there they are. Potassium nitrate, SQMs at the top, SOP granules in the middle, and SOP prill at the bottom. At the end of 3 days, 4 days, and 6 days, you begin to see that potassium nitrate is solubilizing into the paper. Sulfate of potash in a granule or a prill do not. So the dissolution rate of potassium nitrate is greater than potassium sulfate. So once again, doing a quick overview, when we're talking about the right potassium fertilizer selection, looking at sulfate, let's go back and talk about chloride sensitive crops. Avoid chlorides. Now we've got the sulfate containing crops, or the products. Salinity sensitive crops, avoid excess sulfur and chloride. Even though they are essential to the plant growth, excess is not good. Limit the sulfur supply to the demand of crops, especially in semi-arid or arid areas or under saline growing conditions, and when using irrigation water of poor quality, saline water. So a summary of potassium nitrate and sulfate of potash is that potassium nitrate has favorable plant nutritional composition. It has a better performance because it's more soluble. Full range compatibility with other fertilizers, most agrochemicals with potassium nitrate products. With nitrate, once again, cation uptake synergy, but that companion ion of ammonium can cause cation uptake antagonism. Nitrates can help to relieve soil salinity stress with minimal contribution to soil salinity. Plants fed with nitrate, like we discussed earlier, have a greater water use efficiency. And finally, the uptake synergy between potassium and nitrate is well known. The last point we're going to discuss is salt index. What is the salt index? Salt indices are used in the fertilizer industry to indicate the safety of a product when that specific fertilizer is placed in or near the seed zone. The salt index allows us to compare fertilizers with each other. One note is that the salt index talks about the fertilizer product itself, not the salinity index, which talks about the soil. So that's an important point to remember. Salt index, we're talking about the product. There's two methods that are used to compute salt index. One is an old method that was developed in the 1940s. Most soil testing laboratories don't use this, or fertilizer testing laboratories for that matter, don't use this, but there are a few that still do. The most current is the electrical conductance method that was developed in the 50s and then further enhanced in the early 2000s. We'll take a look at the first method, which is the soil solution osmotic pressure developed in the 1940s. You'll be able to see that this is a fairly crude way of measuring soil solution osmotic pressure. You take a mix of fertilizer and air-dried Norfolk sand, which I'm in North Carolina. There's plenty of Norfolk sands in eastern North Carolina, but if you're in the Salinas Valley, no, they're not there. And then they would water this until the 75% max of moisture holding capacity, and then held for 5 days. 5 days. In soil solution would then be analyzed for freezing point, and freezing point lowering values were converted to an osmotic pressure by table, and then the salt index was derived from that equation. The second method is a simple laboratory method where it's measured by electrical conductance rather than osmotic pressure. Just taking the fertilizer solution and the sodium nitrate solution and going from there. Much faster, much easier. So as a comparison of the salt indices, if you look at the old method, potassium sulfate, potassium nitrate, they were pretty analogous. Nitrate was a little bit higher salt index, but if you look at the updated, more accurate version, they're pretty analogous. Potassium sulfate, shows a little bit higher salt index than potassium nitrate, but not nearly as high a significant deviation as what you saw in the old method. The newer method is more modern and is more accurate. Most fertilizer testing laboratories use the newer method, but be aware that the old method is still out there, so check with your laboratory to make sure they're using the latest version of salt index derivation. As I said, you can see the comparison of the electrical conductance levels used by the new methodology. So as a recap, to calculate the salt index of the fertilizer, the electrical conductivity method, or what you may see on a test as EC, should be followed, not the OP. If you see a test showing the OP method, might want to take a look at another laboratory. When the main potassium conducting fertilizers compared with the EC method, potassium nitrate shows the lowest salt index, partial salt index, and EC level of the other fertilizers, potassium-based fertilizers there. As I said earlier, the salt index is not the same as the soil salinity. Adding products that have high salt indices can contribute to an increase in soil salinity, but the testing method does not look at soil salinity, just the product. Brief recap of what we discussed. We talked about the overview of common potassium sources. We described what the companion ion was. We looked at those common potassium sources, SQM's potassium nitrate, MOP, SOP, and potassium thiosulfate. And we also discussed the potassium source effect on the salt index. Are there any questions? Thank you very much for your time and interest. Hope to visit with you soon.